video, we're going to go over Dalton's law of partial pressures, and actually we're going to be able to apply it to the concept of collecting a gas over water, which is a lab that you guys are going to be doing in class. So Dalton's law of partial pressures is actually awesome because what it tells you is that the total pressure that's exerted on a system, that equals the sum of all of the individual pressures that gases exert. So for example, if you have in the atmosphere oxygen, nitrogen, helium, all the different gases, they do not interact with each other, which we saw when we're talking about ideal gases. They're not going to be attracted to each other. So instead, all of their individual pressures simply add up together to give you one total pressure. So that makes a really easy problem for us. So let's look at an example. It tells you air contains oxygen, nitrogen, carbon dioxide, and trace amounts of other gases. What is the partial pressure of oxygen at 101.30 kilopascals of total pressure if the partial pressure of nitrogen, carbon dioxide, and other gases is 71.10, 0.040, and 0.94 kPa respectively? Well, I know my total pressure is 101.30, and I know the partial pressure of all the other guys except for oxygen. So I'm going to add up all of their pressures plus the partial pressure of oxygen. So all I have to do to figure out the partial pressure of oxygen is take the total pressure and subtract from it the partial pressure of each of the other gases. And that gives me a partial pressure of 21.22 kilopascals.
So to tag on to Dalton's law of partial pressures, which allows us to add the total partial pressures, all of the partial pressures of gases that are present in a container or in a situation, and that would give us our total pressure. We can also use mole fraction. So the first thing I've got to do is explain what a mole fraction is. So all a mole fraction is simply a fraction of the mole that you are concerned about. So for example, if I have moles of A divided by the total number of moles. So for example, if I had 2 moles of A and 4 moles of B, then my mole fraction would be 2 divided by 6, because I have 2 moles of A and 4 moles of B. That would be my mole fraction. So it would be 1/3, and you could actually get a decimal for it. So it's that simple. So the way that you can use your mole fraction is that your partial pressure, so let's say, for example, your partial pressure of A is going to be the mole fraction of A, so the number of moles of A divided by the total number of moles, multiplied by the total pressure. Okay? And so this is useful because if you know the relative number of moles, you can, and you know the total pressure, you can determine the partial pressure of each of the substances that's in a solution of gases or that's in your container. So let's look at an example. It says if a steel container holds 3.50 moles of hydrogen gas and 3.5 moles of helium gas and the total pressure is 4 atmospheres, what is the partial pressure of each of these gases? So if I want to determine the mole fraction of hydrogen first, what I would do is I would take the number of moles of hydrogen, which is 3.50, and divide that by the total number of moles, which would be 7.00 moles. Okay, so that's the mole fraction of hydrogen. And to determine the partial pressure of hydrogen, I would then just multiply by the total pressure, which is 4.00 atmospheres. And so the answer you get for this is 2.00 atmospheres. Now it asks for the partial pressure of each of the gases. Well, the cool thing is you happen to, it's a coincidence that in this problem you have equal moles of hydrogen gas and helium gas. So the partial pressure of each of them are going to be equal. So 2.00 atmospheres for hydrogen gas and 2.00 atmospheres for helium gas. Now notice the partial pressures based on Dalton's law of partial pressures, the partial pressures of these two gases are going to add together to give you the total pressure. So 2.00 plus 2.00 gives you 4.00 atmospheres.
So if I am for some reason collecting a gas over water, and you're going to be doing this with lighters and releasing gas, you're going to be allowing the gas to be released right over water and collecting the gas in a graduated cylinder. Well, the partial pressure of the gas that you're releasing, plus the partial pressure of water, that equals your total pressure. So that's just Dalton's law of partial pressures. So let's look at an example. Okay, when magnesium reacts with hydrochloric acid, a volume of 0.355 liters of hydrogen gas is collected over water at 26 degrees Celsius. The vapor pressure of water at 26 degrees Celsius is 25 millimeters of mercury. If the total pressure is 7.52 millimeters of mercury, how many moles of hydrogen were collected? Okay, so imagine what you're doing is you're allowing this reaction to occur. It's occurring right over, the gas is being produced right over water, simply sometimes for safety purposes or whatever it may be. The only issue with collecting it over water is the fact that water itself is going to have a pressure. Well, that's not really an issue because based on Dalton's law of partial pressures, I know that the total pressure equals the partial pressure of the hydrogen gas plus the partial pressure of water. Well, I know the total pressure in this case is 752, and I know that the partial pressure of water is 25. And so that tells me that the partial pressure of hydrogen gas is just going to be 727 millimeters of mercury. So that's the only new concept in this entire lesson, is the idea that the two partial pressures add up to give you a total pressure. Now, it's asking me how many moles of hydrogen gas were collected. Well, I have the partial pressure of hydrogen gas, or just the pressure of hydrogen gas. I have the volume. I have the temperature. I can use my ideal gas law. But in order to use my ideal gas law, I need to get into millimeters. I need to get out of millimeters of mercury and into atmosphere. So I'm going to put millimeters of mercury on bottom. Atmosphere is up top. 1 atmosphere is 760 millimeters of mercury. So I know that my partial pressure of hydrogen gas is 0.95658 atmospheres. Now I can plug that in to my PV equals nRT, my ideal gas law. My pressure is 0.9568. I know my volume is 0.355. That equals, well, I'm solving for my number of moles, times my R, times my temperature. Remember, temperature has to be in Kelvin, so I'm going to add 26 degrees Celsius plus 273, and that gives me 299. So when I solve for my number of moles, I get 0.0138 moles. Okay, so all of these ideas that we've been coming up with, that we've been discussing, start with the ideal gas law, and then they're just little branches off from it. So for example, figuring out the molar mass that we did 2 videos ago, right? Figure out the moles, take the mass, divide by moles, there's your molar mass. Using it in stoichiometry problems, figure out the number of moles based on stoichiometry, then plug that value into your ideal gas law, your PV equals nRT. And then in this case, if I'm collecting a gas over water, knowing that the partial pressure of the gas is simply going to be the total pressure minus the partial pressure of water, then plugging in your pressure into your ideal gas law. So all of these different ideas are coming from and are using your ideal gas law, or PV equals nRT.